Welcome everyone to today's Multi-Agent Systems talk. My name is Stefano Albrecht, and I organize these online talks together with Michael Wooldridge. I'm just going to spend a couple of minutes to give you some context for what we're doing for those of you who are new here or who are watching this online. So this talk series is organized by the Multi-Agent Systems Special Interest Group, which is part of the AI program at the Alan Turing Institute. And the Turing Institute is the UK's national AI and data science organization. So the interest group was formed actually following a symposium which we held in February 2020. And the idea of the symposium was that there's a lot of multi-agent systems research happening in the UK, and the UK is one of the early contributors in this area. But over the years, it's become kind of fragmented. So we were hoping to bring the community together, map out the landscape of who's doing what and who's who. So at this meeting, we had over 100 delegates from different labs in the UK at universities and industry. And it was a very interesting and rich experience, lots of talks and discussions. And so unfortunately, shortly after that, things went downhill with the world, but we've been trying to keep it up with doing these online seminars. And the idea is that with these online seminars, we want to give PIs in the UK an opportunity to present their labs and their research activities. Basically, there are three main things we're doing in this interest group. We are organizing the symposium. We're trying to have more of these in the future when the circumstances are a bit better again. And in the meantime, we're doing the online talk series. One outcome from the initial symposium was a virtual map on Google in which we pinpoint all the major labs in the UK, which you can see here, and including some basic details for each lab. So if you're in a research group in the UK, in industry or at a university, and you'd like to be listed in this map, then please reach out to us and we can add you. And lastly, we created this mailing list at the Turing Institute, which we use to advertise relevant opportunities for multi-agent systems research. So at the bottom of the slide, you can see the URL, which takes you to the main page. We also record all the talks that we're doing in this online series, and we put them up on our YouTube channel. So if you just go on YouTube and you search for Turing multi-agent, you should be able to find it quite easily and watch the talks online. And lastly, I want to announce something new that we just started. So we're actually doing a new journal special issue on multi-agent systems research in the UK. And in a similar spirit, the idea here is that we want to showcase the major research activities in multi-agent systems research led by UK-based groups. So if you're leading a group in the UK that has lots of activity in multi-agent systems research, then please consider submitting. This will be published in the AI Communications Journal, and the deadline is end of April next year. So the URL at the bottom is a little bit long, but you can contact us as well, and we can send you the URL as well. We sent out the call with the details recently in the mailing list too. So we're hoping to get together some nice papers here. And with that, I'm now happy to hand over to today's speaker, who is Dr. Amit Chopra, and he's a senior lecturer at Lancaster University. So thank you very much, Amit, for joining us today, and I look forward to your talk.
Thanks very much, Stefano. And thanks. I'm grateful for the nice audience. 20 people. That's an order of magnitude more people than I've had at some tutorials and leading conferences. So that's great to see. Today's talk is about multi-agent vision for distributed systems, and I will motivate a notion of programming, which I call information-based programming, because it is based upon the meaning of communications. And what the message that I want to convey in this talk is that traditionally, multi-agent systems, we've adopted ideas from distributed systems. We've adopted their middleware, we've adopted their techniques, their ordering, and so on. But I think really distributed systems is a fundamentally multi-agent sort of thing, in the sense that the techniques that we are developing in the multi-agent systems community, they are sort of fundamental to distributed systems, to the general conception of distributed systems. And I hope that's the message you take away at the end of this talk. So I'll begin by motivating a kind of system which will be familiar to people in multi-agent systems. The idea of a socio-technical system. The idea is simply that it is a system where you have multiple autonomous real-world principles who engage with each other via software and other technical resources, for example, the IoT, for example, and so on. And these are commonplace socio-technical systems. Any system that involves engagements, that supports engagements between multiple autonomous principles is a socio-technical system. But you'll see that they're commonplace in health, finance, and business. In health, if your healthcare interactions typically involve multiple entities, your GP, for example, hospitals, insurance, laboratories, and so on. Finance, when institutions are trading, naturally multiple institutions are involved in the trades. There are settlement agencies and so on. And in general, the notion of business is a fundamentally sort of social activity, and you can conceptualize it as a socio-technical system where autonomous parties are engaging to conduct business transactions. Now the key thing is that autonomy means that any engineering approach must support loose coupling, and loose coupling means that the approach should support independent decision-making by the principals, and it should support arm's length engagements, not the notion that is familiar to us as computer scientists, the notion of invoking somebody, invoking a procedure. That's not the correct notion when you have autonomy. What you have is you have arm's length engagements via asynchronous messaging. You send one principal sends a message to another principal, and sees what comes of it. And loose coupling also means that principals must be able to change relevant software independently. So this is the idea of loose coupling. And another important point that stems from autonomy is that the approach should support flexible decision-making by principals. And this has been a big point in mass research, especially on protocols and norms and commitments, that traditional approaches often constrain the kinds of interactions that can occur between autonomous parties for technical reasons, for correctness or realizability and so on. So how can we reconcile flexible decision-making with all the technical properties that we want, correctness of the interactions, interoperation, which is something that autonomy also is sort of the flip side of autonomy. You want the principals to be able to interact flexibly in accordance with their own policies, but at the same time, you want them to be able to interoperate and sort of correctly engage with each other. So if you look at traditional approaches, the traditional approaches, take the requirements from all the stakeholders who may be the principals, and think of them as the users of the system, and develop a central software machine. Now, the central software machine in current sort of paradigms, you may see it realized as a web service or a workflow, some kind of platform. And what multi-agent systems approaches have advocated, and especially what I've been working on, is the idea of interaction is the idea that if you have a socio-technical system involving autonomous parties, the way to support it in software is to realize it as a decentralized multi-agent system where each principal is represented by an agent, and they interact on the basis of contracts. Think of them as bundles of norms for the purposes of this talk. And these norms are enacted over interaction protocols. And the messages are carried between the agents via an asynchronous communication service or infrastructure. This is sort of the basic structure we have in mind, that this is what a decentralized mass means. Principals represent agents representing principals, and the agents interact with each other via messaging, asynchronous messaging, on the basis of some rules of encounters, contracts, protocols, and so on. And one of the fundamental sort of ideas in this area in how we model norms, how we model interactions in general, is that when you think about communication, is the meaning that matters if you want to support flexible decision making, not the relative order. And this has been a mass tenet since Yolam and Singh's work on commitment protocols since 2002. So let me give you an example here. So traditionally, if you want to model an interaction between a buyer and a seller, you would write up a protocol as this state machine in the picture, in the slide. You could say that the seller sends a quote to the buyer. The buyer may accept or reject the quote. If the buyer accepts the quote, the seller delivers, following which the buyer pays. So this is a state machine. There are other. This is the interaction rendered as a state machine. Such interaction specifications, also known as choreographies, and they're generally what Yolam and Singh pointed out is that these choreographies are inflexible because they specify a rigid ordering of the messages and leave out other possible sort of interactions. So, for example, what about pay before accept? So here in this choreography, pay happens after accept, but why not payment happening before accept? So imagine if a buyer wanted to do that, why not? Or why not pay before deliver? So this choreography supports deliver first and then pay, but why not? Why shouldn't pay? Why should we restrict the interaction so that pay happens only after deliver? Why not before? And so they had the idea that instead of specifying ordering, what we should be doing is specifying the meaning of the communications. And they conceptualize meaning in terms of social constructs, such as commitments. So for example, you could specify here that quote creates, the meaning of a quote is that it creates a commitment from the seller to buyer that deliver will happen if payment happens. So this is a declarative sort of abstraction, and there is no implication that deliver should happen before pay or any particular order in which the events should occur. It just says this is the meaning of these messages, that quote creates the commitment that deliver if pay, if payment happens, then deliver must happen. That satisfies the commitment. If payment doesn't happen, then never happens, and the commitment expires and delivery need not happen, for example. But still, a seller could deliver if he wanted to, even without payments, right? So it sort of captures interactions very flexibly. Now, if you look at distributed systems research and practice in general, it's largely the opposite take. The work in distributed systems ignores meaning. They have thought about meaning, and I'll come to that point. But in the dominant paradigm is to ignore meaning and to provide sort of application agnostic ordering and reliability guarantees in the systems communication infrastructure, in the applications communication infrastructure. So think of a socio-technical system as realizing some application, some use, right? So that's the sense of the application. And current approaches in distributed systems tend to focus on packing in mechanisms in the communication services. So for example, if you look at TCP, it provides reliable FIFO delivery. That has nothing to do with the application itself, with that you're building on top of TCP, but it just provides, it's just packed into TCP. Message queues do the same, but the unit of communication is messages. And in general, there's a notion of middleware, variety of middleware types that people have constructed over the years with stronger guarantees, for example, causal delivery, and so on. And the idea is just to pack in mechanisms, ordering mechanisms, and with reliability thrown in to sort of support the ordering, with the aim of making programming easier. So it would be intuitive. A few years ago, I would have thought it's TCP provides ordered delivery, and what else is there to sort of, what is to critique about it? We all want FIFO ordered delivery. Why not? It makes programming easy. I don't have to care about the order in which messages come. TCP takes care of some of that. So it's motivated, such infrastructures are motivated from ease of programming. But if you sort of examine them more closely, it turns out they violate the end-to-end argument, which is a fundamental argument of the systems community itself. And the argument basically says that the guarantees that a service provides may be inadequate for the application's needs. And so because these are application agnostic, right? So they don't really know what the application needs. And so whatever guarantees they may provide may be inadequate for the application needs. That means the application must then take steps to ensure correctness at the application level, or to ensure the desired interactions at the application level. And the guarantees may not only be inadequate, but they may actually interfere with application needs. So they may rule out choices that are perfectly reasonable at the application level, but because the service, the infrastructure has some mechanism, it imposes a model upon the application, which rules out certain possibilities in the application. So it rules out choices at the application level. So here is an example of the inadequacy of delivery guarantees. So normally we have, in TCP, if you think of delivery guarantees, it does it by retransmissions and acknowledgements. If one TCP endpoint sends a message, or sends some, let's think in terms of messages. It's a byte stream technically, but let's think in terms of messages, that it sends a message to another endpoint. If it doesn't get an ACK, it'll do a retransmission till it gets an ACK for a certain period of time. So that's the service communication infrastructure level guarantee. And this guarantee actually turns out to be inadequate because what an agent that's sitting on top of something like TCP, two agents that are sitting on top of TCP, what an agent really wants to know if other agents have seen or quote unquote processed the message. So here's an example that shows what I mean here. So here there's depicting an interaction between the patient, physician, and pharmacy. And the patient has a complaint, makes a complaint to the physician, sends a message to the physician. The physician can then write out a prescription and send it to the pharmacy, and the pharmacy can fulfill the prescription and send it to the patient, right? So there's simple enough interaction. Now, if you think about it, the patient may consider it a fault if it times out waiting for fulfill from pharmacy. So the patient makes a complaint, and now it's expecting to receive something from the pharmacy, some medication from the pharmacy. So the fault from the patient's perspective is that it times out waiting for fulfilled. It hasn't received it yet. Now, it doesn't matter if, at the TCP level, the messages get across. The patient's complaint may well have gotten across to the physician, but the patient has not received the fulfilled. So the patient has to do something at the application level to take remedial action. For example, it may send a reminder to the physician by retransmitting the complaint, in response to which the physician may either forwards a copy of the prescription to the patient saying that, hey, I acted upon it, or an ACK, at least, to the patient that I received your complaint, I've seen it, which is not the same as an ACK at the TCP level, because that's happening underneath the agents, below the level of the agents. Or they could introduce, we could introduce other requirements, a commitment requirement, so that the fulfillment happens in a timely manner after the prescription. We could introduce a commitment, appropriate commitments to sort of capture that. So we are introducing these application level mechanisms to take care of the fact that the patient is timing out or waiting for fulfill from pharmacy. And likewise, the other agents could adopt similar strategies. So clearly, having TCP does not help. The patient must do something else in its own logic to handle this fault. So that sort of demonstrates the inadequacy of delivery guarantees in the infrastructure. But what makes the delivery guarantees redundant, in fact? So if you think about delivery guarantees in the infrastructure, like let's say in TCP, in a TCP-based infrastructure, then the delivery guarantees work between the two TCP endpoints. But what we want is an end-to-end guarantee between the patient endpoint and the physician endpoint. They both have each have a TCP endpoint, and there are delivery guarantees that work between them. But what the patient wants to know is whether the physician endpoint has seen the message and acted upon it. And therefore, we introduce mechanisms like reminders, forwards, and application level acts and commitments and so on. Now, these cover the entire path from the patient endpoint to the physician endpoint in both directions, of course. And they encompass the path of the infrastructure. So whatever application level mechanisms you build subsume the, or make the infrastructure level mechanisms redundant, because they only work, because the application level mechanisms spans the entire path between the logical endpoints of the application, which encompass the infrastructure endpoints. And because delivery guarantees turn out to be redundant, this can potentially hit performance. Of course, sometimes you can have infrastructure mechanisms for performance. If you can show that it leads to better performance, you can put some mechanisms in the infrastructure. But the likelihood is that because the delivery guarantees in the infrastructure are redundant, they potentially hit the performance of the application of the multi-agent system. Let's look at why FIFO ordering guarantee turns out to actually limit choices at the level of the agents, at the application level. So imagine that now FIFO ordering is, like I said, is commonplace, right? When we build applications, we build them over TCP or message queues or something like that. So I think FIFO ordering is actually, in a way, sort of the holy cow of messaging, right? But but it really interferes with flexibility at the agent level. It restricts their choices. So suppose, imagine that the physician was sending prescriptions to the patient, to the pharmacy over a TCP connection. Now, let's say it sends two prescriptions, one after the other. Now, any two prescriptions are independent. They'll have different identifiers that which sort of captures their independence. So they're causally unrelated. They can be handled independently by the pharmacy. But if you send them over a TCP connection, if the first prescription is lost, the second prescription won't be let through by the TCP connection because it tries to guarantees FIFO ordering, right? And that interferes with the patient's, with the pharmacy's flexibility. It does not let it handle the second prescription that it could have handled. There's nothing that prevents it from handling the second prescription, except the fact that TCP is enforcing FIFO ordering. The TCP connection is enforcing FIFO ordering. But this is a simple example. I think you'll all buy that. If there are two prescriptions, then they can be handled independently. There's no particular order in which the pharmacy should receive it. But let's look at a more interesting case where the communications are causally related. Let's say the physician can send a prescription and then send a cancellation of that prescription, right? So a cancellation causally depends upon the prescription because it refers to the prescription. So a physician can only send a cancellation after sending the prescription. But does a pharmacy have to receive the cancellation after receiving the prescription? It doesn't have to do that. In fact, you could argue that it's better for the pharmacy to receive the cancellation before receiving the prescription that's being canceled, because then at least it doesn't have to do the work it ordinarily would have to do to handle the prescription and then do the cancellation. If it gets the cancellation first, it's actually better from the pharmacy's point of view. You could argue like that. So that there is no need for the pharmacy to receive a prescription strictly, a cancellation strictly after the prescription. It can get it before. And if it gets it before, there's an identifier in the cancellation which refers to the prescription. So when it gets the prescription later, it can just ignore it, right? So it's perfectly reasonable. And that's what you would imagine happens in practice. And that's what meaning sort of refers to, meaning refers to sort of what is the significance of the communications to users, right? And that is what they take into account in their decision-making via the agents in this case. And ordering is ordering, like FIFO ordering, it's a sort of meaningless approach because you're not looking at the content of the messages. You're just ordering messages because that's a traditional way of thinking about consistency in distributed systems, ordering and so on. By the way, I'm happy to take questions if there are any. So message ordering, in fact, which is the idea that the nodes of a distributed system observe messages in orders consistent with some global order. So that idea is actually unsuited to decentralization and to decentralized multi-agent systems, because think of, I've already motivated to you that ordering in the infrastructure limits choices at the application level. But also think about the fact that messages convey information. When mechanisms in the infrastructure are motivated from ordering, hold back a message from an agent to enforce that ordering, what you're doing is holding back information from the agent. And ordering limits flexibility by delaying the arrival of the information. So that's the effect of ordering. It limits flexibility because it does not let information arrive at an agent upon which it could have acted. And therefore, the only reasonable constraint, really, if you're thinking about coordination in a decentralized multi-agent system, is this. We should ensure that message emissions are correct. If a message emission is correct, then its reception, whenever it happens, is correct. That is the only sort of reasonable constraint we want to enforce in a decentralized multi-agent system. We focus on message emissions. We ensure they're correct, and then it's guaranteed that receptions are correct whenever they happen. And that means that there is no need for any ordering anywhere in the system, in the ordering of communications in the system. So programming languages also address the topic of how they approach distributed systems from the standpoint of how can you program a distributed system? What is a good programming model for distributed systems, for concurrent systems in general? And therefore, there's a lot of interest in messaging-based paradigms as opposed to shared memory paradigms for coordination, and protocols as an and protocols. And these approaches typically assume FIFO messaging. So they already have one drawback in that they assume FIFO messaging. They sort of bake it into the system. Erlang and Go do that. Erlang is, of course, an older language. Go is a newer language designed by Google. But there are some nice things about Erlang and Go. I like the fact that they are promoting messaging-based coordination, because that's just a step away from protocols itself. So the nice thing about Erlang and Go is that they promote communication between processes, Erlang and Go processes, via messaging. There's work in programming languages on session types, which takes it further. So it's not gotten into practice yet. It's not part of Erlang and Go as such. But what session types try to do is they recognize the fact that if you just try to do things without specifying the coordination, maybe you'll end up writing the messaging-based coordination incorrectly in your endpoints, in your processes or your agents. So what they do is they enable specifying application-specific protocols. So you could look at the healthcare setting or a business setting and specify a protocol relevant to that setting, and then the protocol could be verified for the presence of bugs, deadlocks and progress and so on. And in addition to that, they support a programming model that, given a protocol, then you could extract skeletons from it that enable programming the endpoints of the system or the agents of the system. So they have certain nice, the motivations are certainly nice. But the problem with session types is that they lift ordering to the application level. So, ordering does not work in the in the infrastructure of the system, in the infrastructure communication service of the application, because it limits flexibility. But session types lift this sort of flawed idea to the application level. So I'll give you an example here. Suppose, so in session types, you can specify a global protocol, and here's a payment protocol with 3 roles. Seller, C is, I think it should be K, not C. K is the bank, and B is the buyer. So the seller can send an offer to the buyer, and semicolon means sequence. So after which the buyer can send an accept to the seller, after which the buyer can send an instruct to the bank, instructs the bank for payment, after which the bank can transfer some amount from to the seller. So this is the global protocol. And from this global protocol, you can extract algorithmically a skeleton for the seller. So what the seller sees from this protocol is that it sends an offer to B, after which it gets an accept from B, after which it gets a transfer from K. So this is a projection from this global protocol. This is the seller's role from this global payment protocol. Now, if things go like this, where the seller sends an offer, the buyer sends an accept, the buyer sends, and the seller receives the accept, the buyer sends an instruct, and the bank sends a transfer. Now, if the seller sees the accept before the transfer, things are great, because that's what the projection is expecting, that accept from buyer and then transfer from the bank. But actually, because even if you have FIFO, an enactment like this could happen. Even if you have FIFO channels, which session types assume, an enactment like this could happen where the transfer from the bank arrives before the accept from the seller. Now there's a problem here, that the seller is expecting accept first and then transfer, but it could transpire that transfer arrives first and accept later. So the way, that to me is a problem. But the way session types get around the problem is by saying that, hey, we are going to ignore, we are not going to look at the bank's channel, at the channel from the bank. We'll just look away because we want an accept first. So we're going to look at the channel from the buyer and just focus on that. So now it could happen that the transfer arrives, but the seller is not going to look at that because it's waiting for an accept. But the transfer could actually bring the information that the seller needs to actually ship the goods. The accept may turn out to be redundant, so there's no need to wait for it. So what session types do is, by picking particular channels to look at, depending upon what the order happens to be in the projection, they also delay the information from arriving, and they limit the flexibility of the seller in this case. That the seller could have acted upon the transfer, but the transfer won't be seen by the seller till it has seen the accept. So I think the point so far I've been trying to make is that traditional coordination approaches in distributed systems and programming languages, they're built upon the notion of ordering. And how can we get away from this idea? How can we enact multi-agent systems over something as simple as UDP, for example, right, which provides no guaranteed delivery, it provides no ordering guarantees. So could we do that? If we could do that, there's and if we could do it conveniently, engineer multi-agent systems over UDP, that's great, because our system runs on a very simple infrastructure, UDP, and we can do exactly, we have no interference from UDP because UDP is so simple, so minimal, it imposes no model upon the application as such, upon the agent, so it won't interfere with their flexibility. So how could we get to that point? And Murinder Singh, who's a frequent collaborator of mine, actually made an important breakthrough with the idea of information protocols. So instead of specifying the way information protocols work, I'll give you an example, in fact, 2 examples. Work is that instead of specifying message ordering, you specify the meaning that is relevant to the users, to the agents, in terms of information causality, which is the idea that what an agent, the communications an agent can send depend upon the information it has received from earlier communication. So that's the idea of information causality. And integrity is a simple idea that in any enactment, you can't have conflicting values for the same thing. Like, for example, if you're transacting for an item, if a buyer and seller are transacting over an item, then if the item value is, I don't know, fig in some enactment, then it can't be jam in the same enactment, because now you have two conflicting values for items in the same enactment. So that's the idea of integrity. A basic idea, it basically captures consistency in decentralized settings, that you can't have two values for the same thing in a decentralized setting. And what the great thing that follows from this is that the constraints are only on message emission. You apply causality and integrity constraints on message emission. And as long as the emissions are correct, they happen according, the protocol is safe, you can verify the protocols. As long as the emissions are correct, then the messages can be received in the order that they're delivered by the network. You don't have to pick which message to receive when. The agents don't have to pick. They're just delivered, and they're part made of the agent's state. And then the agent can take further action, send further messages, or whatever internal processing it needs to do, depending upon what is there in its local state. And then there's the, I'm not talking much about norms in this talk, but meaning is not just at the sort of information protocol level. Meaning extends to whatever is relevant, whatever the information content of the message communications is. And like I hinted earlier, the content could be commitments, that some messages are creating commitments and discharging commitments and so on. And so these higher level abstractions could be layered on top of the information protocol. The information protocol are sort of populating the base level events in the local state of the agents, and the enactment of the information protocol populates events in the local state of the agents. And then based on these events, you can infer the higher level events, like commitments being satisfied and violated and so on. So it's very modular and elegant in that way. And then if you think about the agent itself, it yields an architecture like this, that the agents are enacting information protocols, and there's an interpreter for the information protocol sitting inside each agent, which ensures that enactments happen in compliance with the protocol. Now, this adapter abstracts away from the network. It's like actual emission to the network and actual reception from the network. It's abstracted away completely from the agent. What the agent developer does is write a decision-making module, which uses an information-based API exposed by the adapter. So basically, the agent's developer, the way the developer writes programs is, the developer asks, what messages can I send at this point, depending on what the adapter has seen. And the developer gets back a list of messages, and the developer can apply business logic to decide which of those messages it wants to send, right? So it becomes a information-based API. The network API is abstracted away, which is great. And I'll come to this point. Ideally, you don't want to be doing receptions in the decision-making of the agent. You want to abstract away from receptions, because you can in the information protocols framework, and because you should, because ordering receptions is so that your agents work correctly and so on is a very difficult thing to do. So here's an information protocol in the language called BSPL, the blindingly simple protocol language. And this protocol demonstrates it specifies the scenario of over here, that the bank sends, the seller sends an offer. Now, the thing to realize about an information protocol is that the keys specify the integrity constraints. So for any value of key, the other parameters of a key parameter, which is the ID, the other parameters can have at most one binding, right? Because we don't want conflicts or bindings like I explained before. So that captures integrity. And the parameters are in addition adorned in, out, or nil. And these specify the information dependencies, the information causality. So for example, the seller can send to the buyer an offer message. To send the offer message, it can create bindings for ID, item, and price. That's what out indicates. You can generate bindings. To send an accept to the seller, the buyer must know the ID, which is what in indicates, that it should already know from prior interactions, presumably in this case from the offer, from having received the offer, it'll know the ID. So it should know the ID, item, and price, but it can generate an account. And the buyer can also send to the bank and instruct. To do that, it needs to know the ID, price, and account, and it can generate a binding for inst. And the bank can do a transfer to the seller. To do that, it must know the ID, price, and inst, and it can generate a binding for OK. So these are all parameters: OK, inst, ACK, and so on. And so you see the causality over here. That accept, the buyer can only do an accept after an offer because it needs the information that offer is generating, the information that is there in the offer message. So the buyer must receive offer before accept. The buyer must send an accept before sending an instruct, because it needs to know the binding of ACC, account, from accept, from doing the accept. And the bank can only do the transfer after receiving the instruct, because it needs to know the binding for inst, which is in the transfer, and out in the instruct. So you see how causality is constraining the emissions, but the receptions themselves are unconstrained. So the buyer sends an accept, the bank concurrently can send a transfer, and they can arrive in any order. There are no constraints whatsoever in the order in which the accept and transfer are received. And therefore, this enactment and this enactment, they're both valid, and without having to jump through any hoops, such as, don't look at the buyer, or don't look at the bank's channel till you've received from the buyer. So you're not trying to receive particular messages at particular times. You just, any message that comes at any time is okay. Let me see how I'm doing for time. Okay, so this is a treatment protocol. Let me skip this in the interest of time. I just wanted to point out a thing about Erlang, and in general, programming languages that promote messaging-based coordination. So these languages have sophisticated reception primitives, and the thing I wonder about if that is a good idea, because you can write a receive primitive like this. The receive primitive in Erlang has this sort of structure that you can receive a message indicated by pattern 1 when guard 1 is satisfied, or you can receive, and so you can have a list of these patterns, and Erlang processes have a mailbox in which the messages are kept, and the receive patterns applied to that mailbox. And as if you find a message that matches the pattern, then you execute, and the guard, then you execute the body. Now, having a receive like this, and then application developers use this receive construct to receive messages in certain orders. But the idea that to let the application logic pick which messages to receive when, sort of schedule the reception of messages, is an idea that is at odds with asynchrony, with the fact that messages can arrive in any order. They arrive in a non-deterministic order. And therefore, it's generally not a good idea. It's a sort of a brittle idea. It can break down very easily. And I think that's why messaging-based coordination without protocols is not easy. I think it's a bit of a trend these days. People think locks and other shared memory abstractions for coordination are difficult to manage and do properly. and they come up with messaging-based coordination, but they are not easy either. And in fact, Tu et al. Have done a study of Go programs that demonstrate this. The messaging-based coordination is not much easier than using locks or shared memory coordination. And really, it makes you wonder if there should be native support for protocols in information protocols in programming languages, because information protocols, like I tried to say earlier, have this, the adapter for the information protocol, if you sort of build that into the programming language, then it abstracts away from the network API, means it abstracts away from receptions altogether. So an agent never has to do a receive. And I think that could be a really interesting idea. But more broadly, I think meaning-based engineering of decentralized application, and think of meaning as, again, the information content of messages. It's a big hole in distributed systems. They are aware of it. Pioneers in distributed systems, the people who formulated the end-to-end principle, they were aware of it. Cheriton and Skeen's critique of Catox was substantially founded on the idea of meaning. David Clark, in a recent symposium, says that if we knew how to do meaning at the application level, or think of application or model application in terms of meanings, then we could run our applications over UDP. We wouldn't need TCP. TCP is merely a compromise of sorts. And so if you look at distributed systems today, the focus is on middleware and the transport layers, the packing mechanisms, having more flexibility in the mechanisms over there. And they don't focus much on the application. If we look at the mass approaches, like interaction-oriented programming especially, then it by modeling the application in terms of meanings, it sort of does away with these heavy layers, middleware and TCP. And then you can run your application directly over the internet. And that's an exciting possibility. And I just want to mention some themes for further research. Information protocols are fairly new, and we certainly need more expressive information protocol languages, for example, that support unbounded enactments where two agents can go, offer, counter, offer, counter, offer, counter, offer, back and forth for an unbounded number of steps. We need methodologies for specifying protocols, including a catalog of properties and efficient verification of those properties against protocols. We need programming models for agents, where we've done quite a bit of work in the last 2 years that take information protocols and expose this nice information-based API for programming agents. We need programming, and like I was saying a little bit earlier, we need programming language support for protocols, and that could be a native support for protocols, where, can you imagine that there could be a programming language that wouldn't support communication unless that communication was specified in the protocol? That's the kind of thing I'm thinking about. And there's other things that will be more familiar to people in multi-agent systems is contract-based computing. So model business contracts via norms and enact them via protocols. And then you could imagine even a higher level programming model, a contract-based programming model, where the agent developer sort of has an API which lets him or her query the local state in terms of which contracts can I, which norms, which commitments can I satisfy, which commitments can I create at this point, and so on. So it could be a programming model based on these high level notions. And then another thing that we started investigating is realization of these programming models on serverless platforms. The idea is to take advantage of the scalability mechanisms in the cloud that serverless platforms is, that they can spawn instances of compute as required. And the benefit for serverless is that it'll enable realizing decentralized multi-agent systems in the cloud. And that's not just to say that, okay, who cares about decentralized multi-agent systems, but you should think about it as a way of managing application state, decentralized multi-agent systems as a programming model based on state, which is a big gap in current serverless platforms. They don't handle state very well. So Yeah, a lot of this work has been informed by in joint work by joint work with Muninder Singh and Samuel Christie, but the opinions sort of expressed in this talk are, they would probably emphasize different things. So the opinions, the stronger opinions, are my own. That's it. Yeah. Thanks very much. Happy to take questions.
Thank you, Amit. This was an interesting talk. It's you don't personally, I don't often hear a lot of talk about agent programming languages, so I was really interested to hear what you had to say. I have one question to kind of start, if you don't mind. So I remember 2019 or so, I think I attended a Dagstuhl seminar on engineering reliable agents, like multi-agent systems. And there was like a relatively strong representation of people working in programming languages, like agent-based programming languages. And there's like a whole subset in AMAs that exists in this space, right? And the one question I had that wasn't really so well addressed to me, like they talk a lot about really interesting features and what could be done here and there. And I think I saw a lot of this in your talk as well. But then the fact is, it sort of seems like it's just not being adopted, right? For example, I don't really see people in my sub-communities that use these agent languages at all, right? It's usually just you code up your own stuff. And when I talk to industry, I don't really see that featured much. They just do their own stuff, more or less. So one thing that I kind of tried to find out at this meeting, and I'm interested to hear your opinion on this. Why do you think is it that there's all this research activity in agent-based programming, but it isn't really adopted more broadly by the community and in practice in particular?
Yeah, it's a good question. I don't think I have a good answer for that. But the way I think about where the agents community started and where it is now, we started from philosophical foundations. We started with ideas, and it's taken a while to get those ideas realized into, for example, languages and programming models, and so on, especially in my work, the work on commitments and protocols. I think it's become mature in the last 10 years. I don't think it's quite something that adoption is a completely different question, right? I mean, there could be many factors that lead to adoption or non-adoption of even good technologies. About agent programming languages in particular, I mean, I'm working on protocol languages, on interaction specification languages. If you think about it, agent programming languages have been focused more on constructing the agents themselves. For example, JSON has a BDI-based programming model. They haven't focused much on communication itself. And what we've tried to do in a recent piece of work is try to bring these kinds of communication abstractions to a JSON setting. So you have the power of using the sort of cognitive abstractions, beliefs, and so on, but you combine them with communication abstractions. And in doing so, you resolve some difficulties with those kinds of programming languages, or you make them sort of more suited to engineering practical systems. So I don't know why they are not adopted. I just think the problems have been hard. People in the 90s, when meaning sort of, when Sheridan Skeen wrote this critique of CATOX, which was a famous middleware, then people started working on the idea of meaning in distributed systems, but they still couldn't come up with a reasonable programming model based on meaning, or a reasonable conception of meaning. And so the problems have been that sort of we are tackling have been really hard. I think that's part of the thing.
Okay. Yeah, I think it's difficult, but we've got more questions lined up. There's a question by Arshad, if you want to unmute yourself and go ahead.
Yeah, thanks very much. Hi, Amit. Thank you very much.
Hi.
Nice talk. My background is a little bit more distributed systems and reliability. And I've just posted something. When you had your example on FIFO delivery, when you were talking about the patient and the doctor and the pharmacy, the notion that I think that was on slide 8, if I'm not mistaken. So some of the notion that you spoke about in terms of FIFO, for example, you mentioned that the pharmacist has to wait, can't deliver or can't service the second prescription until it has. But the notion of FIFO delivery from the distributed systems community is well understood. It's on kind of on a pairwise processor. So, for example, if there is the patient, the pharmacy, and you deal FIFO with that agent, and then it's FIFO on another agent. I suspect what's happening is what you were talking from a distributed systems perspective is more causal ordering. Now, some of the issues you were talking about, I wasn't too sure whether, because causal ordering, you can remove the unblocking, at least some of the notions of blocking that you were talking about, you can remove them by if you piggyback a lot of the historical information on your message, you can remove a lot of those issues that you were talking about having to block, right? So I'm just wondering at what level, or whether your notion of blocking or certain notions of ordering, whether they were as strict as those coming from the distributed systems community. And finally, usually people look at developing a middleware with ordering because what they don't want is to bloat your application. So for example, if I'm working on the reliability part, I don't want an application person having to think about reliability, and you end up bloating your application just to handle. So that's why you end up factoring out all those, let's say, fault tolerance ordering you put into a middleware so that someone working at the application level focuses just on the application. So I wanted to just know some of your views.
Yeah.
Thank you very much.
Yeah, they're both good questions. So in relation to the first one, I'm assuming pairwise FIFO ordering. So in this case, I'm assuming that there's a TCP connection. There's a connection. There's a channel from the physician to the pharmacy on which prescriptions are being sent. So it's a FIFO channel. Now, if you have a FIFO channel, then it's going to be that the second prescription, the pharmacy won't be able to process the second prescription until it has received the first prescription. So that's guaranteed. And now you could say that, well, sort of going away from your point a little bit, you could say, well, I'll open as many channels as there are prescriptions. But well, then you've lost the benefit that you gain from the programming convenience of FIFO, because now each message is its own channel in a sense. So then you're like on par with programming over UDP, and nobody really knows how to do that nicely. There are no good programming models for building arbitrary applications over UDP. About causal ordering, I didn't get your point fully.
Yeah.
So I think. But what is the second part of your question? I'm sorry, I lost it.
Basically, what I was saying is usually for causal ordering, if you want to remove the notion of having to block so that you can process, so usually what tends to be done is you piggyback the history of the given message, right? So like you said, I think in one of your slides you were saying that you need to be able to know where a message comes from, and then you'll be able to deliver. So here, if during any interaction you piggyback the history of that message, right, and then you forward it, right. So then, in some sense, you can you can try to resolve it, right? So in the worst case, you will need to piggyback every single message that has been received before that new message is sent, right? Yeah. But however, it's very rarely the case. Sometimes you just need the very recent history. So I just wanted to know your opinion.
Yeah, I don't know about that specific technique, so I'll let that be. But I remember the second part of your question now. You know, the more interesting one, that you want to separate reliability from the application logic. You want to handle reliability in the service layer, communication service, and that saves the application developer the effort. But that's exactly the point of this example, that the patient has not received a fulfilled from the pharmacy. It sent a complaint to the physician. It hasn't seen a fulfilled. So now that's a fault. The patient perceives that as there's something's gone wrong. You know, why am I not getting a fulfilled from the pharmacy? So now what the patient agent has to do is implement application level mechanisms. It resends the complaint, for example, to the physician. Hey, like, have you seen my complaint? Have you acted upon it? And the physician can send in response a copy of the prescription to the patient, or an ACK at least, that I saw your complaint. So once you start implementing these application level mechanisms, you don't need the lower level mechanisms anymore. You know, so the point is that having network mechanisms for reliability didn't make your life any easier, because the patient had to implement application level mechanisms. So there's no avoiding that in general. And also, because the fact that you implemented the application level mechanism, because application level mechanisms work between the true endpoints, you know, the highest level endpoints, which is the physician endpoint and the patient endpoint. They cover the infrastructure endpoints as well. And the delivery, the acts at the TCP level and reliability at the infrastructure level only work between the infrastructure endpoints. So therefore, they are in fact redundant. You can do away with them, use something like UDP, implement your application level mechanisms for retransmissions, reminders, or whatever else, you know, forwarding and so on at the application level. Then you don't need the infrastructure stuff.
Okay, thanks. We've got one more question lined up from Mirko, if you want to unmute yourself.
Yeah, so thanks for the talk. It is also quite related to the thing that you said at the end. But so I was trying to understand what is the difference between thing that you are proposing and building an application on UDP. Because in UDP, if I build an application on UDP, usually I need to do the thing that you said, like I need to check the state of the message, I need to do retransmission, I need to do like timers and so on.
Yeah.
So it is clear to me that so the thing that you are proposing, because at the end of the day, when you write an application in UDP, you use a state, no? So you need to write a state inside, and the state is semantics.
Yeah.
So at the end of the day, we are doing that, no? So when we are building a UDP application for sending a message between two agents, two hosts, we need to put information there in order that the application level, the application that is reading directly on UDP will do that.
Yeah.
So that is my question. So what is the difference? I don't get this.
Yeah. So the approach I'm recommending is that you specify protocols, and then you have adapters that implement protocols in your agents. These are generic components, and these adapters are sort of interfacing with UDP itself. And what these adapters do is they expose a programming model based on protocols that makes your life easier as a developer.
But my question is that we don't do that anyway now. So because when you write a program, usually what you are going to do, you write a state machine usually that says what you should do if you receive a message, if you have a state machine program. That is one way for working with UDP. The other way for working with UDP will be to have an event-based program that reacts to the type of message that I get. And then again, you have semantics. So that is the two things. So in one case, you have a state machine. In the other case, you have an event-based messaging, let's say. So what is the difference between this and the thing that you are?
Yeah, I think state machines are not a good abstraction, because they for specifying a decentralized system, because what you're doing there is specifying, I'm assuming, orders of messages. And like I've been trying to argue that you don't need to specify orders, because then you're constraining when you're writing your UDP endpoint, some agent, which is the endpoint, you'll be deciding what message to receive when and so on. And that'll make your application inflexible in general.
And for that reason, we use event-based messaging, no? So when the order doesn't matter, we use event-based messaging, where we put the descriptor or the events, like, I don't know, MQTT, something that we use, like we use, that is used around a lot now. It does that, no?
The thing is that if you have a distributed application, then there is a protocol between them. A decentralized mass, there is a protocol. Now the question is whether you specify the protocol or not. If you specify the protocol, then we can use a programming model based on protocols to make your life of programming the agent very easy. Because the adapter, the adapter, which is part of the programming model, will ensure that you don't send incorrect messages. It'll let you know what your options are based on information in the local state, what your options are. It'll do correlation for you. It'll automatically. It'll make sure that any message is delivered to your business logic at most once, so it'll filter out duplicates for you automatically, and so on. So it provides a lot of convenience that if you didn't have a protocol-based programming model, if you just maybe with an event-based programming model, you are assuming some kind of pub sub or some such mechanism for communicating the messages between the endpoints. But just because you have an event-based model doesn't mean you have a protocol. A protocol is specifying the computation, the coordination between the endpoints in the distributed, in the decentralized system. And just having events, it's like saying, I'll do messaging. So it's like that. It's so having protocols.
I agree, but then the thing that you are saying offer accept can be like the logic that you attach to the event. So essentially, if I receive S, I will do offer. If I receive B, I will do accept. So you see, usually when you write an event-based application, you have like hooks that are attaching the type of message or to the callback, essentially. So I see that type, that one-to-one to this, no?
You in general, so you're talking about event handling in general, that you have event handlers and so on. But that's not the protocol, right? If you have a protocol specification,
it is because you have a node, you have how to react, and it is a protocol. I don't know if you want to call it a different way, but it is an implementation of a protocol.
Okay, maybe we can discuss it.
Okay, we can discuss online later. Sorry for that.
Okay. No worries. No, I appreciate your questions.
Yes.
Thank you, everyone, for the questions. I think Arshad, I can see you got your hands up, but in the interest of time, because we're already over the hour, perhaps you can take it offline with Amit. So Amit, thank you very much again for your interest in talking, for answering the questions, and thank you everyone for attending. Have a good holiday break, and we'll see you hopefully again at the next Multi-Agent Systems talk.
Yeah, thanks very much to everybody for showing up, and thanks, Stefano, for organizing this.
Thank you. Bye-bye.
Bye-bye.